Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 3, Lesson 3, where we continue talking about charged stuff. So last time, I introduced the vocabulary words conductor and insulator. And we said that things in the world are not really divided into two categories, A or B. There's really a spectrum, and things fall somewhere along that continuum of being a good conductor and therefore a bad insulator, or a good insulator and therefore a bad conductor. So we're going to go a little bit further with those words, and we're going to talk about conductors in electrostatic equilibrium. Conductors in electrostatic equilibrium. So it's a conductor. It's something on which or through which charges can move rather easily. And we're in electrostatic equilibrium, meaning that the charges are not moving and the net force on them is zero. Okay, so let's see what that means. According to this text here, there are four things that are true. Properties of an isolated conductor. So if it's an isolated conductor in electrostatic equilibrium, let's see what it says. The electric field is zero everywhere inside the conducting material. It says that the electric field is zero inside there. So if it's a conductor and the charges can move, and if the field inside is not zero, if there's a field inside there, and it's a conductor, wouldn't that make those charges move? Yes. So that's why if it's a conductor and it's in electrostatic equilibrium, electrostatic, meaning the charges are not moving, well then of course the electric field must be zero inside. Because if the field inside were not zero, those charges would move. So this field has to go away. In other words, if you read all the words here, this would have been obvious. Electrostatic, the charges are at rest. Well, if the charges are at rest, of course there's no field inside because the field would cause them to move. Any excess charge resides entirely on its surface. So if I have a conductor, and of course the conductor is made of matter, and if the conductor is made of matter, there are billions and billions of charges all over it. But the plus charges and the minus charges cancel out, so we can think of it as neutral. If there's extra charge, if there's an extra 3 minus charges, they're not going to stick around here in the center. Because if they do stick around here in the center, they're all the same and they repel each other. And if that's the case, then they will repel each other and they will move until they're spread out. Well, while they're moving, we're not electrostatic. But once they get moved out here and they reside on the outer surface, then we're static. So any excess charge resides on the surface. So again, if you read all the words, there's the key. If you read all the words, that's obvious. The electric field just outside is perpendicular to the surface. So if I have, again, my conductor, if there's a field, and if I have any electric charges out here, if there's a field outside that's perpendicular to the surface, that's fine, because it might tend to make this charge, a field pointing this way would push this charge in, but these guys would push it back, so it stays there. A field this direction would push positive charges this way, but this negative charge would get pushed this way. But we're assuming we're surrounded by a vacuum or air, not a really good conductor, so it's not going to move through them. And what if I had a field pointing neither into or out of, which is okay, but to the side. Well, wouldn't that cause us to move? Yes, it would cause it to move, but we're static. Oh, so this can't happen because we've got an electrostatic situation. Again, if you'd read all the words, number 3 would have been obvious. What is point number 4? On an irregularly shaped conductor, the charge accumulates at sharp points. So I've been drawing regularly shaped conductors for you, things kind of like circles. What if I draw an irregularly shaped conductor? Now I'm just going to show you the picture in the book because whenever I try to draw this, I draw it wrong. So this is an irregularly shaped conductor. And what it's saying is the charge accumulates at sharp points where the radius is smallest. So this is considered a sharp point. This is considered not sharp, blunt. And it says that the charge accumulates here. You see how the charges are close together here and far apart here? And that's because if these guys push each other apart, they move apart. If these guys push each other apart, they don't move apart because it's pointy and there's not really any place for them to go. So that one's a little less obvious. You have to do a little more than read all the words. You have to figure out what the picture is that it looks like. But I just wanted to go through all of these because the first time I read this section, I thought, oh, these things are all, oh boy, how do I remember all that? And then I kept going back to the title and reminding myself, oh, if I read all the words in the title, then this is obvious. So read all the words. A life lesson, to be sure. So again, we are still in AP Physics 2. We're still in Unit 3, and this is Lesson 3. That was conductors in electrostatic equilibrium. Now I would like to demonstrate for you something that we call an electroscope. And it's just a fun little tool. And then I'm also going to show you how to draw it on your paper, because sometimes people don't do a very good job of drawing it, or sometimes people look at a drawing and they don't understand what the parts mean. Chamomile tea. So sometimes we have fun objects in our lives, like a balloon. Yay, here's a balloon. And I thought I would show you that my balloon is not charged. And one way I can show you that my balloon is not charged is by taking something like this piece of string, which is also not charged, and showing you that they don't really attract each other. The balloon and the string don't exert forces, which makes sense. But remember how I showed you induction last time? What I'm going to do is I'm going to charge the balloon by rubbing it on my hair. And then without touching the balloon to the string, I'm going to show that the balloon can attract the string. So I'm going to rub the balloon on my hair. I've got this thing that erases the board behind me. Got all this stuff on it. Let's see. Okay, I'm going to clear that. Now I'm going to change my background so that you can see better. Choose my virtual background. And I'm going to choose none. There you go. And now you can see the messy board behind me. But now when I put the balloon over here, you can still see it. Okay, so now I'm going to rub the balloon on my hair. It's not going to work all that great today because I have a little bit of gel in my hair. But let's see. So we rub the balloon on my hair. Remember, the balloon is rubber and my hair is like fur. And so now you can see that the balloon attracts my hair, which means that the balloon is charged. All right, now let's see what happens to the charged or to the neutral string when I bring the charged balloon near it. Watch. Do you see that string being attracted to the balloon? Yes. And again, that's not because charged things attract neutral things. No, the charged thing is inducing a charge. It's causing the charges in the neutral thing to rearrange. So there's a positive side and a negative side. And the closer side attracts the balloon. And all of a sudden, and we can't, I got to charge it up again. Here we go again. And, oh, look at that. Look at that. Isn't that fun? So anyway, that was demonstrating induction. Now, another thing we could use if I don't have a string lying around is I could use this. And this is an electroscope. And you're like, no, it's not. It's an Erlenmeyer flask. Okay, it's an Erlenmeyer flask. I'm going to set my balloon down. I'll have to recharge it later. So all this is an Erlenmeyer flask. And then I've taken a piece of copper wire and balled up one end and let it hang down. And then on the inside, there was a student who had a sandwich wrapped in foil. And I just stole a little bit of foil from the student's sandwich. And there are two pieces of foil there hanging right next to each other. Now, this is called an electroscope because what it's going to do, let's see if you can see it well there. What it's going to do, oh, I don't need this piece of paper right now. Just a sec. I'm going to make my picture bigger. And that's not it. Screen sharing. How do I stop sharing my screen? There we go. Basic. Oh, there we go. There we go. There we go. Stop sharing my screen. Okay, so now this is, oh, my hair is bigger. Okay, so now I think you can see this better. So what I'm going to do is I'm going to charge the balloon and then bring it close up here. And if I bring it close to this thing and the balloon is charged, it will cause the charges to separate top and bottom. And if this end becomes charged, these two little pieces of foil should separate. So let's see if I can make the foil inside separate. Here we go. Here we go. Did you see those pieces of foil moving? Yes. And then they moved for just a second and then stopped being moved. That's, I think, because some of the charge jumped over. We'll talk about that in a minute. Okay, nice charged balloon. And separate, unseparate. And then what ended up happening is that the charge jumped off of the balloon. It was like I touched, and then the charge moved away. Anyway, but this is called an electroscope. And all it does is it shows us if something is charged when I bring that charged thing nearby. They separate, they unseparate. They separate, they unseparate. Okay. Fix my hair because that's very important. Okay. Now we want to see my piece of paper again. There's my piece of paper. So to draw an electroscope, all you need to do is, draw your little Erlenmeyer flask, right? And your little ball up here, and your two pieces of foil. That's all you need to do. And then what we're going to say is, if I bring something positively charged, let's bring something negatively charged first. I bring something negatively charged, you'll see why. What that's going to do is that's going to send negative charges down here, and there will be a negative end and a positive end. And these negatives repel these negatives, and the little pieces of foil separate. Now, the problem, the funny, annoying thing that happens is when I drew these negative charges, sometimes when I draw two negative charges next to each other like that, people are like, oh, it's an equal sign. Okay, it could be an equal sign, but in this context, I don't know why there would be an equal sign hanging around. In this context, these are negative charges, not an equal sign. I don't know what equal would mean there. Equal signs only mean something when I have something on the left and something on the right. A equals B. Equals is like walking around saying is, are, doesn't mean anything. All right, so that's what would happen if I brought a negatively thing nearby. I did that first so I could turn them into plus signs. If I bring something positive nearby, then all the minuses would get attracted up here. There'd be a minus side up here, and there'd be a net positive side down here. Either way, I get a separation of charge, and these two pieces of foil are charged the same way, and therefore they separate. And this is called an electroscope. It's a tool that I can use to tell if something is charged. It doesn't let me know if the charged thing is positive or negative, but it does let me know if it's charged versus neutral. All right. Now, there's a fun word that we use in science, and this is a great time to demonstrate. Oops, I went away. It is a great time. Goodness gracious, I'm pressing the wrong button. For me to talk about what that word means. I like my virtual background. Okay, the word is quantization. Which is kind of like the word quantized. First of all, the word quantization and the word quantized sounds fancy until you realize, oh, it sounds like the word quantity, meaning amount. Right? What quantity? You know, I'm going to the grocery store. I'm going to buy bananas. What quantity of bananas would you like to purchase? 4, please. Okay, so quantity, how many? So if I go to Baskin-Robbins, which is a happy event, but if I go to Baskin-Robbins and I say, I would like to purchase 1.5 scoops of ice cream, they're going to look at me like I'm crazy. And although there are lots of reasons to look at me like I'm crazy, that's not one of them that I want to encourage. So I have to buy 1 scoop of ice cream or 2 scoops of ice cream or 3 scoops of ice cream or even 0 scoops of ice cream if I'm not in the mood. But I can't buy 1.5 scoops of ice cream at Baskin-Robbins. Scoops of ice cream are quantized, meaning I can only buy them in either the smallest amount, a scoop, or integer multiples of that smallest amount. Shoes are like that. I suppose I could buy a shoe. I could definitely buy 2 shoes, but I can't buy half of a shoe. Half of a shoe doesn't do anyone any good. So there are things that have a smallest amount, and then you can buy integer numbers of that, or you can have integer numbers of that. And then there's other things that aren't quantized. For example, time. It seems like time is quantized because tick, 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 on our watches, the second. But are there smaller amounts of time than the second? Yes, we can divide a second into fractions. But we joke about the size of families. We could add up the total number of people who live in La Crescenta and divide by the number of houses and apartments, and that would give us, 2.7. Oh, the average family in La Crescenta is 2.7 people. We're very average. There's 2.7 people living in our house. No, there aren't. You can't have 2.7 people living in your house. So it's funny when there's something we know is quantized, like the number of people, and we treat it like it's not. Okay, so what is quantized in physics? In physics, what's quantized is mass and charge. And it might seem like, when you're, weighing out crystals in your chemistry lab, that you can have any mass you want. But remember, those crystals are made of atoms. So if you get really small, if I'm talking about carbon, I can have 1 carbon atom or 2 carbon atoms or 3 carbon atoms. I cannot have 3.5 carbon atoms. And therefore, mass is quantized. Same with charge. Charge is quantized because I can have the amount of charge that's on 1 electron, or twice that, or 3 times that. But I can't have 3.5 times the charge of an electron. I just can't. So mass and charge are quantized. And this was just a good time to mention that principle. All right, the final thing I'm going to talk about today is what we call ratio problems. And these are just problems that tend to show up on tests. And they seem really hard unless you realize, oh, there's an easier way to do that. For example, let's say we're talking about charges, and we've learned recently about the electric force exerted by a charged thing is K Q1 Q2 over R squared. That's called Coulomb's law. I know you know that. Well, what if I have 2 charges here, Q1 and Q2, and they exert a force They exert a force on each other. Ooh, on each other? What does that mean? It means this one pushes this one, and it means this one pushes this one. The force between them, what? So this one exerts a force of F on this one. I'll call it F naught. This one exerts that same number of newtons of force, F naught, on that one. Now I'm going to change some things. Let's get out a different colored pen. So now I'm going to change some things. I'm going to double the amount of charge here, but I'm going to divide the charge here by 3. Oh my goodness. Divide charge by 3. Double the charge here. Divide the charge by 3 here. And I'm going to triple the distance between them. Wow. That's 3 changes. There's a lot going on. So I start out with these 2 charges and the force between them, or they exert a force on each other. This one pushes this one with a force F naught. And therefore this one pushes this one with that same force F naught. If I make all 3 of these changes, what's the new force that this one exerts on this one? Which is the same way of saying what's the new force that this one exerts on this one, or what's the new force between them? Wow. How do you do a problem like that? Well, I call it a ratio problem because we started out with something and we changed and we want to know what's new. So what I'm going to do is I'm going to put a big old fraction bar and I'm going to put 1 old and new. I'm going to put 1 in the numerator and 1 in the denominator. So I'm going to do the old in green because I originated with green, and I'm going to do the new stuff in purple. And in general, fractions are easier when you have a big number on top and a small number on the bottom, but I really don't know. I'm going to assume that because I'm tripling the distance, tripling the distance, they're farther away and that distance gets squared. I'm going to assume that the new force is small. I might be wrong, but that's my guess. So I'm going to put it in the denominator, and I'm going to put the old original force in the numerator. And what that allows me to do is if the answer comes out to be 7, I can say, this over this is 7. I can say the original force is 7 times as big as the new force. So I just like having numbers that are bigger than 1 in the numerator. Not a big deal. So this was the original force. So I'm going to write K Q1 Q2 over R squared. That was my original force. And then I changed things in purple. So I'm going to write the new force in the bottom. It's still an electric force, so there's still a K. Q1 got divided by 3. So now I have a charge, not Q1, but Q1 over 3. This got doubled, so my second charge is 2Q2. And my original distance was R. My new distance is 3R. And that whole distance is squared. Do you see how I got this answer? Well, that's not an answer yet, but do you see how I got this collection of letters that I'm going to simplify to be an answer? The problem said we started out with what's in green, 2 charges repelling each other. And then I said, hey, if I double this amount of charge and I divide this amount of charge by 3, I lessen it, and I spread them apart so they're 3 times as far away, what's the new force? Right? That's what I said. And the original force was called F naught. So now what I'm going to do is I'm going to see this over this. Is what fraction? So I started with this force, and my new force is K charge over distance squared. K charge 1/3, charge twice as much over 3 times as far squared. So what I see is that the K's cancel, and the Q1s cancel, and the Q2s cancel, and even the R squared cancels. Wow. And all I'm left with in the numerator is 1. And in the denominator, I have 2/3 over 9. Do you see that that's a 9 because it's 3 squared? You see it? And then 2/3 over 9 is 2/27. 9 times 3 is 27, which is 27/2, which is 13.5. In other words, the new force, I'm sorry, the original force is big. The new force is small. This is 13.5 times as big as this. The original force is 13.5 times as big as the new force. That's what I mean when I say a ratio problem. When there's an original thing and a new thing, what they're really asking you to do is express both of them in the same fraction, one in the numerator, one in the denominator. And there's going to be a ton of stuff that cancels, and then you just deal with the numbers that are left and interpret your results. So we frequently do that with things like forces or distance. Anyway, they show up all the time. If any of these steps didn't make sense, I'm happy to talk about that if you ask me about it in class. Until then, I hope you have a fabulous day and don't break any of the laws of physics.